Welcome back everyone. In today's video, I'll be explaining AtCoder Beginner Contest 323. I'll explain the problems from C to F. I've provided the correct Python codes in the video description, so please check it out after you've listened to my explanation. Let's get started with problem C. We are given a list A of scores of n problems and a list S indicating which problems each player has already solved. Our target is to determine how many more problems each player needs to solve correctly to get the first place. Firstly, we should compute the current scores for each player. We put the value into list B. Don't forget to add a bonus score. Then we know the bonus score taking the minimum of B. To exceed the border score with the minimum choices of the problems, they must select problems in descending order of scores. Therefore, we should prepare the list T and its value consists of a score and the index of the problem, and sort T in descending order of the first value. Now that we have finished the processing, we solve this problem for each player. For instance, we focus on player 1 in this example. Let x be the current score of player 1 and count be the number of problems he will solve. In this situation, x doesn't exceed the border, so he tries to solve the problems in the order of list T. First, we have problem 3 with the score 2500. But he has already solved it, so he skips the problem. Then we have problem 2 with the score 2300 and he didn't solve it yet. Therefore, we add x to 2300 and increment count. However, x doesn't exceed the border, so we continue the process. We will do the same thing for the next. Then x becomes greater than the border, and count is the answer for player 1. We repeat this algorithm for all the players and get the full answer. However, be careful here. If x equals border from the beginning, this means that the player is already in the first place, because the base scores are all different because of bonus scores. So in this case, the answer for the player is 0. This ends the explanation of problem C. Let's proceed to problem D. We have many slimes of different sizes. Two slimes of the same size can be put together. Our task is to minimize the number of slimes after putting them together as much as possible. Then the most important thing to solve it is to know that slimes can be split into some groups so that any of the two groups are disjoint. This is because for each slime there exists the unique smallest possible slime size that can transform into it after merging. We call the smallest slime base slime. So the problem can be split into groups of base slimes. In this example, we focus on the base slime of size 75. Then our next concern is how to manage the number of slimes in group 75. I strongly recommend you use binary numbers. For example, when we write 101011 in the binary system, it means that there is a slime of size 2400, no slime of 1200, one slime of 600, no slime of 300, one slime of 150, and one slime of 75. In this way, we manage the number of slimes as one binary number. But what should we do when adding other slimes to the group? For example, consider 3 slimes with size 300. Then we do a prime factorization-like process to 300 and get 75 times 2 squared. So we've realized that they belong to group 75. Then we just add 2 squared times 3 to the current management number D of 75. Since a carry of the addition means the merge of slimes, it automatically lets us know the current state of slimes. Therefore, for each information of upcoming slimes S and C, we just do this calculation in red ink. Isn't it so simple? Yes, it's very effective. After adding all the slimes, we'd like to know the number of remaining slimes. It's also easy because we compute the pop count of each management number. This ends the explanation of D. Let's proceed to problem E. We continuously play songs by randomly selecting from N tracks. Our task is to determine the possibility that track 1 will be played at time x plus 0.5. The most challenging part of the problem is to determine what to calculate. It's difficult to consider the state at time x plus 0.5 directly, so let's think about the state just before it. Therefore, we define dp of I as the probability that the music just stops at time I. Then, dp of I can be calculated in ascending order of I. Let's see the example. First, we initialize dp of 0 as 1. Considering the next time the music stops from time 0, we will reach dp of 3, dp of 5, and dp of 6. So we add 1/3 to each. Then we reach dp of 3 following dp of 1 and dp of 2, and we can move from dp of 3 to dp of 6 using track 1. So we add 1/9 to dp of 6. In this way, we complete the list dp in ascending order of time I. Finally, if the music stops between 6 and 4, it stops between 4 and 6, we can hear track 1 at time x plus 0.5, which is 6.5 in this example. So the answer is the sum of the probabilities times 1/3 to select track 1. This is the outline. Precisely, the transitions and the answer can be written in this way. And the time complexity is like this. This ends the explanation of problem E. Let's proceed to problem F. we are given three coordinates in xy plane representing the start point, the position of cargo, and the goal point. We move the cargo only by push. Our target is to determine the minimum number of movements to bring it to the goal. This requires extensive case analysis but does not need any difficult algorithms. We have many initial configurations in the problem, but firstly, we get started with this example. So, we are considering the cases where we only need to push it up or to the right. In these cases, we generally have two options to achieve the minimum. One is pushing the cargo up and to the right, illustrated in blue. The other is pushing to the right and up, illustrated in green. We will calculate both and take the minimum of the two, but for now, we focus on the blue route. We divide it into pieces. First, we must move to the point below the cargo. Then, we push it up and reach here. Go around to the left, and finally push it to the right. Therefore, the whole route is split into 4 small movements, and all of them can be calculated as Manhattan distance. I'll repeat, but we are considering the cases where we only need to push it up or to the right. However, there is an exception. Here's the case. If YB equals YC, we don't need to push the cargo up and move below of it. Therefore, the best route in this case is moving to the left of it directly and then push it to the right. So we need to adjust the calculation method based on whether YB equals YC or not. And moreover, here's another exception. Given the same positions of the cargo and the goal as the above example, but suppose that the start is on the right side of the cargo. Then we must go around to the left side of it. In this case, we require 2 more actions. This happens if YA equals YB and XB is less than XA. So we must add this condition here. The same thing happens in the case of the previous slide. So we must add this condition here. Now we've completed the calculation for the blue route going up and then to the right. So far, we have been discussing how to solve the problem under the assumption of a specific configuration. Well, how about other configurations? In fact, they can be reduced to the first configuration. I'll explain this. First, we align the cargo to the origin by translation. Then, by reflecting the x-coordinate and the y-coordinate, we can move the goal into the first quadrant. In this way, the case is reduced to the case where we only need to push it up or to the right. Finally, returning to the initial diagram, and recall that we need to calculate the green root. In this case, swapping the x-coordinate and the y-coordinate is effective. After that, the green root becomes what we have calculated, so we just do the same process. Then, the answer is the minimum of the two roots. This ends the explanation of problem F. With that, I've completed all the explanations. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.